Us today. Thanks, Sayan, for recording. This is the ibpsa-usa Research Committee webinar series. I am Gokul Paranjoti. I'm the chair of the webinars working group for the Research Committee. And our presentation today will be on skills for tackling built environment challenges by Dr. Clayton Miller at the National University of Singapore. This webinar is hosted by the ibpsa-usa Research Committee with the goal to share new ideas from research to the building simulation community. If you have questions during this webinar, please type them in the Q&A window. At the end of the presentation, I will unmute our audience on Zoom for a discussion with Clayton. You could also try to chat the panelists with questions, but I would prefer that you type it in the Q&A box just for uniformity. I think that's pretty much it. I have a couple of announcements after the presentation before we get to the Q&A, just for those who are joining us right now. And with that, I will hand it over to Clayton for his presentation.
Great, thank you, Gokul. I appreciate the introduction. Welcome, everybody. I guess good afternoon and good evening to a majority of you. I'm here in the future. It's Friday morning for me, 7 a.m., so bright and early. Thanks a lot for the introduction. Thanks to the ibpsa-usa Research Committee for the invitation, to Alex and Gokul and the team. Today, I'm going to dive into, as Gokul mentioned, sort of generically skills, tools for tackling built environment challenges, kind of a generic title, I would say, but specifically, it's kind of a discussion diving deeper into the concepts of scalability and generalizability, which I'll define here in a second, don't worry, and why I think it's important in that context of transforming our field. Before I get started, I'll go ahead and post again in the chat a link that people can download the PDF of the slide deck. I find that this is sometimes helpful for a lot of people because there's a lot of links. And if you want to dive deeper into something while I'm presenting, that's really helpful. And as well, you can see here on the screen, there's a QR code, which I'll also pop up at the end when the Q&A and acknowledgements part. A little bit about myself. As you can tell from my accent, I'm not originally from Singapore. I grew up in the middle of the U.S. in Nebraska. You went to the University of Nebraska, an architectural engineering program. Worked in Omaha, Nebraska for a couple of years. Decided needed to get out and see the world, and actually moved to Singapore at that point in 2009 to do a Fulbright grant, focused actually on Energy Plus sort of development with some NREL folks and LBNL folks as well. And then I stuck around, worked on a startup company where I really started diving into the concepts that I'll present today, kind of the machine learning and data science side of things. Decided to do a PhD, get into academia in a sense at the ETH Zurich in Switzerland at the Institute of Technology and Architecture, and made my way back to Singapore in 2017 in the job I'm in now, back in the Department of the Built Environment, where I did my Fulbright, in fact. If you're not familiar with NUS or the Department of the Built Environment, we're very proud to be among some of the best departments focused in built environment technology. So something like architectural engineering that you see in the US, but also basically the engineering side of the architectural, construction and design industry. My team itself, you can see here, we call ourselves the Building and Urban Data Science Lab. Our goal is to try to converge the data science and building science communities as much as possible, kind of steer these two massive ships closer to each other, help both of these communities understand each other better, the terminology, the challenges, et cetera, which I think you'll see in the presentation today. You can see a few photos there of my team. We are, a lot of the group of my team are engineers, but also have experience in architecture, computer science, data science, and things like that. You might remember me from an ibpsa webinar a couple years ago where I stood up on my soapbox and really talked a lot about Python. And I'll talk a little bit about Python today. Trying to encourage people in our community to learn how to code. It's actually that the tools and the methods for learning are becoming better and better and better. And so if you want to check that out, actually, there's a link there that you can follow to look at that slide deck. In that presentation, I made the analogy of learning how to code as similar to learning how to cook. And I compared coding to Power BI and Tableau and Excel, which I made the analogy that, you know, we all have different choices of what we eat for meals. Basically, we either cook, we go to restaurants, or maybe we do something very fast. And I think data analytics is something similar. So this presentation is designed to kind of build upon this momentum. But if you didn't get a chance to see that presentation, you can check out that slide deck. So building upon coding skill in general, here are the buzzwords, right? These are the things that you read about when you read the news or anything about data science, big data, machine learning. I should add chat GPT to that, or whatever, the new kind of techniques that are out there. These are all buzzwords. We hear these a lot, but what do they mean for us? What are some of the things that we can learn from these applications of these concepts in other industries? And that's what I want to talk about really first is like the built environment and construction. Let's compare that to other industries that we might be familiar with. The only main one we'll look at today is automobile manufacturing, so cars, basically, right? Here's a nice photo of an assembly line, probably in the 1950s or 60s. A lot of the digital innovations that I just mentioned in the last few slides have really been applied to this industry, because if you look at a factory, a modern, brand new factory today, you can see that the automation of construction, let's call it, of a car is very, very digital, and it's ubiquitous. And there's a lot of techniques that are being applied to the design, the building of the cars, and also the way the cars operate in the real world. So in that sector, you have engineers, just like we do. You have engineers, designers, and they spend a lot of time designing cars, designing a model of a car. And as soon as that design is somewhat perfected and tested, you take that design and you mass produce that object, right? So you have assembly lines, you have systems that are fully optimized for that specific design. So, and I know I'm preaching to the choir, but it's something that I want to make a very strong emphasis on, is that our industry, the built environment, is way different, right? We have engineers or designers or both, or of course both, and they design a building, but that building is really kind of what would be called in the manufacturing industry a prototype, right? It's designed in a very customized way. You got all of your other designs of the rest of the building stock, and you have to basically, most of the time, create individual designs for those buildings. So when we think about digitization, we can't think about it in the same way. It's a completely different paradigm. We actually have a much bigger challenge in some ways. Because of this, unique nature of each building being a prototype, we have rich architectural diversity, more or less. I mean, depending on where you are, what city, what the culture is, what the building is, right? These are all iconic buildings. Of course, I kind of cheated. I put a bunch of really interesting iconic buildings here, but we want buildings to be different. We don't want to mass produce buildings. That's not going to make our cities lovely places to visit and live. But because of this diversity, we have an efficiency problem. We have a big challenge with, this is kind of the symptom of what I'll be talking about, is that the efficiency of per hour worked for manufacturing, for example, has basically doubled since 1995. The total economy has gone up by over 150%. And the construction industry is still kind of just barely nudging its efficiency levels up year by year. In fact, even somewhat peaking in the last 10 years. So they say, this is an Economist article from a few years ago, saying that we would be $1.6 trillion of value better off if the efficiency had even just matched the productivity growth of manufacturing, basically, is what the comparison is. So let's embrace this key reality of our industry that everything we do is kind of prototype driven. So the big challenges are the scalability and generalizability of the machine learning techniques, the modeling techniques, the different types of things that we do. These are big, messy challenges, and I'll define these two words here in a second. So this is what we really need to think about. We can't approach the problem in the same way as the car industry, for example. So what's scalability and generalizability? Scalability, they're very related terms. There's a lot of overlap. In fact, I think it's not black and white. Scalability is the ability to apply a technique across a diverse building stock or occupant population. So think about your fault detection, think about your modeling techniques, your data, even just data collection, collecting data from buildings in a scalable way is super challenging, as a lot of people know. Generalizability has a little more of a tint towards the machine learning or prediction side. So the ability for a model that's trained on a certain set of data to adapt to be accurate for new incoming unknown data from a previously unseen sort of scenario, let's say. Or I guess, the training data could be related to this unseen situation, but generalizability is on the modeling side. So these two concepts are, I think, similar. They're related. There is some differences. In my opinion, I say scalability is, the technique or the data collection process across the building stock. Generalizability is the ability for machine learning to be accurate across a diverse stock. So now that we've sort of defined those, what's one application of this, or what's one example of this? So let's look at energy prediction, which of course this is ibpsa, so a lot of people here are going to be very familiar with this. But first, let's go back to our comparison of the car industry. Let's look at an example where they've really tackled this well. There's another Economist article a couple of years ago showing the growth of investment of quote unquote AI, which is machine learning in a certain sense. If you look within what sector has the most investment, at least at that period, 2018, 2019, autonomous driving is at the top of the list. This is from our friends at the car industry developing self-driving vehicles, right? So it has the most investment at this time. And so if you think about what autonomous driving relates to, one of the key components is really advanced computer vision. So a car has various sensors and cameras and different types of mechanisms to observe what's around it, but it needs to identify what the things around it are. It needs to understand if it's a threat or if it's something that the car needs to address. So computer vision is extremely important for autonomous driving. And I'd like to believe that the catalyst for a lot of this work is from the research community in this particular area. So one of the large major reasons for innovation in computer vision is actually a data set called ImageNet, which was developed starting about 10 or 12 years ago. It's a large data set of images, millions of images that are very simple, kind of everyday things that have the image, and then it has a tag. It has a ground truth label of what's in that image. So here you can see on the right cars and dogs and frogs and trucks and different things. And this data set was created and labeled at a lot of effort and cost. But the innovation really came with using this data set as a mechanism to test the generalizability of machine learning models. So, ImageNet had a competition starting around the time it was generated in 2011. And every year they held this competition to understand, or to basically people would compete, different teams, different researchers would compete to bring down that the error rate of predicting what those images contain, basically. And year upon year upon year, it got better and better and better to the point where by 2015, the solutions were actually performing better than a human would, a human just looking at the images and identifying what's in that image. So, and in fact, around 2013, 2014, I believe, is where some of you might have heard of deep learning, right? This is a buzzword that's become very commonplace. That's really where, in that competition, is where deep learning wasn't really invented, but it's kind of where it became well known. It became, people saw that it was the main solution. and it really grew very fast. So the innovation, I'd like to draw a correlation between all of this investment in innovation and of course, self-driving cars are not perfect, but a lot of it I think was a catalyst. What behind that was this competitions and open data sets. So let's come back to the building industry. How about us? What do we do well? What do we not do well? Well, for machine learning specifically, we love case studies. We really do. And I'm as guilty as anybody in the research that I've done, especially with building simulation models, white and gray box models. We use case studies a lot because we have a certain building that we're focused on. We collect the data, we do the analysis. This is great in some ways, but at the same time, we're not getting a sense or understanding of how generalizable or scalable these techniques that we're developing are. So about 4 or 5 years ago, we got together a bunch of us from ASHRAE TC 4.7. Chris Balbach kind of led the way, kind of blazed that trail, brought me on board. We said we need kind of a ImageNet style competition and data set for buildings to create more conclusive results through the application and understanding comparison of techniques on the same relatively large building set. So some of you might have heard this is, or if you're not familiar, I'm hoping that you'll check this out. We developed what's called the ASHRAE Great Energy Predictor Competition 3 that was hosted on the Kaggle platform. If you're not familiar with Kaggle, it's a really amazing place to learn data science and compete in different machine learning competitions. There's several even $1 million competitions that occur in different industries and different domains and sectors and data types. This was the first competition using energy data on the Kaggle competition, time series energy data, and it was one of the largest time series competitions, prediction competitions actually that they had at that point. The way Kaggle works is that people will download a large training data set and use it to build models, prediction models. They'll upload their prediction up to twice a day even over the course of the 90-day competition. So that's actually able to tweak and tune and see how they can make their solutions better. And there's a real-time leaderboard which updates over time. And then when the competition's complete, there's actually a whole nother test data set that allows you to see what's called the final leaderboard. ASHRAE was gracious enough to host the competition by providing 25 grand of prize money that was split across the top 5 solutions. And we had lots of contestants. It was really exciting to see lots of people from lots of different sectors and geographical areas and backgrounds who participated in the competition, uploading around almost 40,000 total predictions across the competition. And the cool things that we understood were when you talk about generalizability, that's really what the solution had to be. It had to be accurate. The solution had to be accurate across a large, diverse set of buildings rather than a single building. You couldn't overfit or over-optimize your solution for a single building. So what happened is large ensembles of models actually proved most accurate in that sense. Gradient boosting trees, gradient boosting models, especially light GBM, were the most accurate. These two things are well known, I think, in the data science community, that tabular data and time series data, these two types of solutions are really useful. But I think in our community, people are diving straight into deep learning and not looking at these more simplified solutions. Pre-processing the data was really important. So if you're training your models using anomalous behavior in certain buildings, you're going to bias that solution towards that anomalous behavior, make it less accurate in a generalizable way. So engineering was necessary. The top teams had a bit of metering experience and knew how to remove certain parts of the data set. The top 5 solutions are widely available. You can download them off of GitHub. There's lots of explainer videos that the winners provided. In fact, and they also provided solutions that are more simplified than what they used to win the competition. To win a Kaggle competition requires very complex solutions that take hours, maybe even days to run. They gave advice to people on more simplified solutions, in fact. And the thing that I'm most excited and proud about the competition is that there are hundreds of workflows that were shared through this competition. So these are not the winning workflows, let's say. These are just people that are tinkering around, that are exploring the data, utilizing it in fun ways, using pre-processing and creating starter code in Python So this is really the cool stuff, in my opinion, because it helps people in our community, the built environment community, to learn how to code through looking at examples, looking at sort of recipes or templates for analysis. Another cool study that we just published last year is we looked at the errors of the winning solutions. Where did the winning solutions not predict well? Okay, and this is, you see this bar chart as a breakdown of the classification of error. This is the aggregation of the classification of error. The winning solutions fit really well in about 80% of the data sets across these 1,600 buildings, but 20% was not so good. So we dove into those areas of error to understand, is it even fixable? Is it just a matter of, of course we know that you can never have 100% accuracy, but how could we make it better? Could we add additional sensors, and could we do this and that to make this better? So that's really another cool part. If you're interested in more details about the Great Energy Predictor 3, there's another slide deck here that you can download from an ibpsa Nordic presentation I gave a couple years ago. A cool part about this is that we were able to pull out the data out of the competition and add some data to it to make the data set even larger, which we put out there as the Building Data Genome 2 project, which is now being expanded with a small group of us from the IEA Annex 81 community to create what we call kind of an open data sandbox. And this is meant to be kind of a directory. We don't want to duplicate effort so much, let's say, on the other sources of open data, but we're trying to create just like a directory. And there's actually a website that's being created that's not really ready quite yet, but will be quite soon. So keep an eye on LinkedIn or on other places where we're going to have a place where you can download data sets from all different areas and not just energy data. Another fun and related area is measured data versus simulated data, which I think a lot of you are very interested in because this is the ibpsa community. So I gave a presentation in eSIM Canada where I talked about machine learning versus engineering and physics driven white box and gray box modeling. So it is related. This generalizability challenge is related. So please check that out, but we don't have time to do that today. So energy's great. I think a lot of us focus on energy here because, of course, this is the ibpsa community. But the other paradigm of performance are the occupants, the humans, right? How do we account for them? How do we make their lives better? Which is something we're also interested in. So if we go back to our car analogy, for better or worse, Tesla is one of the great examples out there of innovation. One really interesting there's a couple different articles here about how Teslas will take data during the operation of the car, send the data back to to the cloud, let's call it, and that actually allows the car to make changes based on what people need or want based on the way they drive the car. So it's actually a feedback loop, which is helping to improve the car over time. So in the built environment, we kind of do something in this direction a little bit. There's these really great post-occupancy surveys that, for example, UC Berkeley has created at the Center for the Built Environment. And they collect data to try to understand how buildings operate in the same way that car companies try to understand how people are using their cars. But the problem is that this is a one-time survey. It's static. People are kind of thinking into the past of how they felt. And so obviously there could be improvements in how that works. You combine this concept with what's called the quantified self, the ability for people to strap a watch on their wrist, which allows them to monitor their health and sleep and activity and fitness, and chronic diseases or illnesses or treatment of chronic diseases such as diabetes and epilepsy and things like that. It's a great series of Economist articles in 2022, which talk about the adoption. You can see on the left that smartwatches have a similar trajectory as things like mobile phones and computers and even electrical power. So we're going to see these more and more become a part of our lives. So we, in my team, in collaboration with UC Berkeley's Center for the Built Environment, so Stefanos Gavan and his team, have been working on a platform we call Cozie. This is an open source platform that you can, the source code is out there. You can spin this out and make your own app using the code. We developed it for Apple and Fitbit platforms. The GitHub link is there if you want to check it out. And Cozie allows us to collect all the physiological data that you can get from these smartwatches, but also create what's called microsurvey question flows. So these are tiny little question flows that nudge people. There's a little vibration on the watch every so often, which it's asked people to answer short questions about how they feel at that exact moment in that exact spatial context. And on a watch, this is called micro EMA, ecological momentary assessments. EMAs are generally done on phones or computers, but micro EMA on a watch allows us to nudge people and kind of interrupt their attention for slightly less, which allows us to ask questions more often and to have higher what's called compliance rates of test participants giving us data. So here you see thermal, visual, and oral feedback. These are very simple 3-point preference questions. But as you'll see in a second, we've expanded on that. We converge those microsurveys with all of the different kinds of data you can find from the watch, from the environment. So of course, you have fixed sensors that are around the spaces, which measure temperature, humidity, et cetera. You can put additional sensors on the watch strap, something we call the strap pack. We get near body temperature and things like that. And when we deploy this, we get data across a spatial context. Here you see these little dots in this frame of a building called the SDE4, Net Zero Energy Building here at NUS. And each of these dots is a person filling out a microsurvey and collecting data from that person at that exact point in time. So our test participants usually are filling out the microsurvey about 100 times over the course of 2 to 3 weeks. So we're getting lots of rich data from each person, but also multiple data points from multiple people in each of the zones, ideally. And these data allow us to create machine learning models that characterize the people and the spaces. A couple really cool things like for example, Mahmoud Abdulrahman, one of the PhDs that just finished, he's using this data to characterize people's spatial proximity to things like windows and fans and diffusers. And since we know exactly where the person is and how they feel, we can train models using their proximity to those different features. So on the right, you see a BIM model that's been decomposed into what's called a graph-based model. And we can use that to improve our prediction of thermal comfort. Here's a quick little fun example that Mahmoud created showing in how that kind of works. And this is you've heard the concept of a digital twin. Digital twins are supposed to be these virtual environments that are running sort of in parallel with reality. So this is something we try to do to show that you could use this type of method as a digital twin. Here you see Mahmoud walking through a building, and the spatial proximity of him to the different objects is dynamic. You see how it's happening. And on the right-hand side, you see that graph model and how the graph model changes as the person is further or closer to different things in the space. So this allows us to improve the accuracy of thermal comfort prediction. It helps us remove the reliance that we have on installing sensors in every single part of the building. We can actually use what we call it kind of humans as a sensor. So these microsurveys allow us to characterize spaces without having to have a sensor there even. So it's not perfect. It's not the same as sensors. You don't get that longitudinal data collection, but you can characterize spaces. This is what enhances the scalability factor. So I talked about scalability, not having to install sensors in every single space across the urban context. Instead, using humans to be that sensor is something that we can use maybe to improve scalability. We don't want to bug people when we don't need to. So Mahmoud also worked on a way to target when and where to collect microsurveys. Sometimes if you're asking the same person the same question at the same time in the same place, you're actually creating redundant data that's not useful in each incremental additional survey. So we want to target things. So he has a really nice paper you can check out, which focuses on that. And then finally, Matthias Quintana from our team worked with Stefano Scavan's team to work on comfort models that he calls cohort-based comfort models. So you've heard of course, the general PMV models and adaptive comfort models. You probably also heard of personalized comfort models. Cohort comfort models are somewhere in between. They're trying to create personalized insights without having to have everybody wear a watch and collect data from every single person. So we use recommendation engine type of techniques. So please check out that paper if you're interested. Thermal comfort is important, but it's not the only thing that matters in the built environment. We also have microsurveys related to movement, sort of why people maybe take the stairs versus the elevator. We have noise, distraction, and privacy, which is the one that I'm most excited about. I think in indoor environments, this is even a bigger deal than thermal comfort for a lot of people. Infection risk perception is another question flow that we created. And we're also taking it to the next level in terms of communicating with the person. So not just taking data from them, but sending information back to the occupant. So we have a study that's ongoing right now where we're learning people's occupant or their preferences using EMAs. We're creating models. We're understanding the context, who they're with, what they're doing. And then we use a technique called just-in-time adaptive interventions, or JITIs, to send them messages that help them improve their situation potentially. So if any of you have worn a smartwatch, you know this because Apple Watches, or for example, I wear an Apple Watch and it tells me to like breathe and relax. I think it knows that I'm stressed out, assistant professor, right? So a lot of these watches tell you to stand up or take a few steps. So it's in that same type of direction. And this is kind of a different type of schematic, a little more complex. There's actually a BuildSys short paper that you can check out which describes this deployment and what we're trying to do. And here you can see some of the data that we've collected from this. So we started last October. We're about halfway through. We're planning to get 100 participants filling out approximately 100 microsurveys. And they're being told to live their lives as they usually do. They're going about their day, going across Singapore, going home, going to the office, taking public transportation, taking cars. In fact, we have a few data points up in Malaysia. Some people went on holiday and are on vacation, and we have data points from France and England and different places. So this is what I mean by scalability. So you're not confined to a single building. You're actually able to collect data across the building stock, regardless of what type of sensors are in those spaces. So it's not perfect. It's not the same as having sensors, but it's something that we think is very interesting to characterize, like I said, both those people and the spaces. Our goal in making this an open source project is that as many people around the world will use it. So we hope that in a few years, people use Cozie or something like it. I've seen a couple other projects popping up using smartwatches. We get millions of data points across hundreds of thousands of people and maybe hundreds of thousands of buildings, right? And we're able to, through this type of scalable data collection, maybe we can create some more generalizable models about occupant behavior. A lot of you in this webinar are probably building simulation models. You're using the occupancy profile from the DOE reference buildings that was developed maybe, 30 years ago or something, right? So better understandings of how occupants use buildings is really the goal. And one quick thing that we've stumbled across like 2 weeks ago was that our Cozie Fitbit, which we still support, but we don't use quite as much, is on the Fitbit, what's called watch face library or store, I guess you call it, because people can pay for some of them, but not for ours. We actually have hundreds of people across the world that have downloaded Cozie Fitbits on their Fitbit watch as a watch face. And these are the data points that we found in our database of people that decided to send the data to the cloud. So we have data all across the world, really cool stuff, really exciting. For research, this is cool, but also there's the ethics side of it. So we can't use it unless it has IRB coverage, but it's cool to see that this is happening, even though we're not even pushing for it. So our goal is to have Cozie Apple and Cozie Fitbit, the version that we created, on these app stores that people can use. But like I said, it's open source. So if you want to create your own app, your own type of question flows, it's very accessible to do that. So I talked a lot about, I think, generalizability, scalability, I think tools, modeling, a lot of this stuff. It's all really great, but the title of my talk was about skills. I think that maybe that's why a lot of you came. So let me get back on my soapbox about learning data science. without the right skills, we won't implement these things. These are not magical things that, you know, you can just hire one person in a big company and they create magic with their machine learning, you know, skills, right? You need also a human capital base to nurture and understand, and even if it's just to understand how to communicate better with the machine learning community so we can hire more of them, or we can convince them that we have a cool set of problems, let's say. Anyway, you get the point. One really telling part of the Great Energy Predictor competition was because it was on Kaggle, basically the user base of Kaggle were the main participants in the competition. So people who had building industry experience were only about roughly 15% of the contestant pool. But on the other hand, the winning teams did have some of that contextual knowledge, especially the first place team. The gentleman who was a part of that pair actually had some metering experience and understood how that worked. But the point is that we had lots of cool stuff happen, but we didn't have as many building industry people as we wanted. So we want to fix that. We want to see how, like I said, bring these two ships closer together. So that's been my mission in my current role since 2017, to teach coding to non-computer scientists. So our undergraduate program here is called Project and Facilities Management. Now it's called Infrastructure and Project Management. So these are sort of business-minded, project management-minded students. They're not computer science driven. They're not even, some of them even engineering driven. Our cohort is majority female, about 70% female, in fact. We're teaching them how to code. We're teaching them, you know, Python, Pandas, Kaggle, Jupyter, all the different tools in a very, very applied way, extremely applied. So like we show them that it's a tool, we show them how to use the tool safely, but then we don't go into all the guts of exactly what the tool does on the inside, right? And I think that that's a paradigm shift as compared to computer science. Our program now is an engineering program as of this year. So our students are also learning sort of basic theoretical computer science as well. And so we're seeing this really nice mashup between very applied and very traditional computer science. Wasn't enough for me to just focus on Singaporean students and master students. I wanted to get this out to the world. So me plus a group of my team members, my research team, got together and created this course, Data Science for Construction, Architecture, and Engineering. Please check it out. It is free to see all the content, watch all the videos, do all that stuff. There is an option to do a verified certificate, which you can put on your CV or something, but that's the only thing that costs money if you want to pay for it. Yeah, check it out. We've had lots of people on there. The differentiator of this course is that it's data science, but applied in the context that you probably might care about. This industry is very broad. Of course, we can't cover everything. In fact, I have been recruiting colleagues to try to create more of these courses that go deeper into different areas like energy simulation. Adrian Chong, for example, is an expert in that area. GIS and geospatial, Philip Bijecki is an expert. So if anyone out there is also interested in this effort, please let me know, because I want to expand. We want to try to expand this possibly. This is across the world. We've had 30,000 plus people. We're really excited about that. Never imagined that this many people would be interested. A lot of people from India, from the US, Singapore, UK, places like that. But 153 regions and countries represented. So really, really cool. And my team is very proud that we were nominated for a prize, an international prize on edX a couple of years ago. We didn't win, but the winner was like a course about volcanoes and like sort of like drones going into volcanoes. So like, you know, how can you beat that, right? So, but we were very proud to be nominated. So in summary, I think we're kind of on time. We've got a little time for Q&A. Buildings are beautifully unique. They're diverse. They're all snowflakes. They're all prototypes. This is a good thing. Trust me. Like as an engineer, sometimes I feel like, oh, we need more efficiency, but like efficiency doesn't have to come at the cost of a rich, diverse architectural paradigm. But because of this, we have scalability and generalizability as major challenges, even more, I would argue, than most other industries or sectors. And it's not just enough to have really fancy models. We need skills. We need digital literacy is kind of a buzzword now that you might see kind of popping up everywhere. That's it. That's what I've got. I cannot take complete credit for everything here. Obviously, there's lots of people involved from my lab, in addition to the collaborators from the Center for the Built Environment and the Singapore Berkeley lab here, as well as ASHRAE, TC 4.7, the Great Energy Predictor Competition Committee, and then a lot of funding from Johnson Controls, in fact, the Open Blue Innovation Lab, Ministry of Education of Singapore, the National Research Foundation of Singapore, and the Berkeley Singapore lab that we have here. So as I mentioned, please download the slides. There's a QR code. I'll post the PDF as well if you want to download if you didn't get a chance to do that. So with that, would love to take any questions. And I think I saw as I was presenting a couple hands being raised. I didn't stop. Maybe I should have, but
no, I think you're fine. We'll take questions in just a second here, but thanks, Clayton. That was an amazing presentation. I loved how much we're able to do with technology, and the world is your oyster, right? Like you can invent whatever, and it's great. So before we move on to questions, I have a couple of announcements. So if you are interested in joining the ibpsa-usa Research Committee, I will post an email here, and you can go ahead and email to that address, and we'll get you sorted. If you have speaker recommendations you'd like to see, I'll also post a Google form here, and you can recommend speakers, and we will consider that as we move forward in this series. If you are watching us on YouTube, this will be available on YouTube in the coming week. Please like the video and subscribe to our YouTube channel. I will be posting that link as well. With that said, big thank you to Clayton again. Our two questions that came up during were about if the recording was available, and if from someone in Europe who said it was midnight. So thank you for joining us from Europe. But Clayton did post that link for his slides, and this recording will be available on our ibpsa-usa's YouTube channel in about a week. All right. So I guess we'll go with the first question.
I think there's open questions in the Q&A that I can see there. Sorry,
yep.
Well, if you
nope,
suggest.
I was gonna go directly to the first question there. If you could, if you're already reading it, great.
Yeah, the one from Yapan Liu, I think. Yeah, so Yapan is looking at possible suggestions for toolkits or resources for big data, 100 plus gigabytes. They've been having memory leak problems using Python packages. Yes, okay, so that is really big data, right? That's a buzzword that you hear a lot. Big data to me means that you can't load the data set into memory of like a pretty high performance computer, right? So if you have 100 gigabytes, obviously you probably don't have 100 gigs of RAM, right? So that to me is my definition of big data, because anything below that, you just need a laptop and some skills, and you can smash out, some interesting things. So I'm not a big data expert by any sense. However, I do know people, and I've read a lot about people that use a lot of the infrastructure that's designed specifically for big data. Python has a lot of that. So I would recommend just kind of diving deeper into that. Every time I have a problem or I need to find something, I literally just Google it, like, Python packages for memory leakage problems on 100 gig plus data, right? And now you have ChatGPT, I think, which I haven't used, but maybe that would also give him insights. But what I like to, personally, when I have 100 gigs of data, even if it's in one file, I use pandas, and I load the file one chunk at a time. So pandas has the ability to load like X number of rows at a time. And I usually take that, I create a quick loop, which basically goes through the file, pulls out the data I need, aggregates it. Almost never do you really need 100 gigs of data. I usually kind of aggregate it and I make it into a more manageable size. I process the data in a way that then it becomes not big data anymore. So that's kind of my hack in a sense. But there's a lot of infrastructure and techniques out there that I'm not familiar with. Keep trying. And if you need to switch to something like Julia or R, I have a lot of colleagues that love R. I'm not, I don't hate R. I think R syntax is weird. I'm not really a big fan, but like R, have a diverse toolkit. I love Python. I promote it a lot, but don't just rely on Python. So look around and see what you can find. Great question.
Thank you for your answer.
Yeah. And then Nick says, I love the edX course. Thanks, Nick. Any feedback? We're trying to update it. That's the problem with doing data science, is that things go obsolete. So we're working on ways to change the edX course. So if anyone's interested, please check it out. But know that I think in the next year and a half or so, we'll probably make some changes to improve it using different platforms and things. Very good. Thanks, Nick. Anonymous
attendee. Sorry, go for it.
Any other resources you can recommend to learn and apply data science to building? So people that are getting started, I suggest Kaggle to them. I think Kaggle is an amazing place to, it's not just the competitions, there's a lot of examples. It depends on how you like to learn. Okay, so the way I like to learn is I like to have a data set that I care about, that I really want to, in fact, that's, if you remember, I mean, you might have saw my ibpsa presentation from last time. I talked about in my career, I ran into these really messy, crazy data sets that people gave me expecting me to not be able to hack into them. In fact, they probably did it to sort of foil me, right? And so I learned how to code because I was like, you know what, I got to figure this out. I want to figure this out, right? So you have this mission, you have this data set that's your data set, and you want to figure it out. That to me, I think is the best way to learn. And then you go out there and you literally find examples of people that have done something that you want to do, but they've done it on a different data set. And you take their solution and you adapt it to your data set. There's a really great YouTube video out there called Everything is a Remix. Google that. It's all about how everything creative out there, more or less, is to people taking previous things and adapting and changing them and making them better for their situation. And that's how creativity really works. It's not some inspiration, that lightning bolt that, strikes your brain and makes you creative, right? So I know that's not really answering your question. It's not specific, but that's the philosophy of how to learn. That's my strong suggestion. edX courses are great, but it's no replacement for just having something you're passionate about learning. It's like learning languages. Like I never learned languages very well because I didn't really use the language. Like I read a lot about it. I took a lot of classes, but I didn't go out there and just use it and order, order French fries or what, you know what I mean? So using and having a passion to do something is really important. It's a little bit of a tangent. Question from Ladan. Thanks for your interesting presentation. How do you see the future of energy modeling in general? Do you think machine learning models will replace them? Very, very good question. So this is the rabbit hole tangent sort of slide deck that I popped in there. This whole white box, gray box versus black box mentality. In that presentation, I like the car industry as an analogy, because the car industry, go back to autonomous driving. Some companies are using data-driven methods very, very heavily because they have access to data. So Tesla is a great example. They collect data from all their cars out there, and they use that to train models for their autonomous vehicles. There's other companies, like I think Waymo, which I'm not sure really exists anymore. Anyway, there's a few other companies that they do it all in the synthetic domain. They create these basically simulation models, kind of physics-based models, and they develop massive data sets using simulation that then they use to train their models. And both companies use some flavor between white and gray and black box modeling. So buildings, I think, are going to be the same way. If we don't have access to the data, we have to create it. We have to create synthetic data. And sometimes synthetic data is very important if you want to model things that don't exist yet. So in autonomous driving, you can't measure this is a silly example. You can't measure probably a giraffe crossing the road because that doesn't happen very often, right? It's an edge case. It's a weird situation. So maybe you need to model that. You need to do that in a synthetic way. For buildings, we use simulation all the time for buildings that don't exist yet. How can you make a data-driven model of something that doesn't exist yet? So I don't think data-driven modeling will replace physics-based modeling. I think they'll work in tandem, and I think they'll work, they'll be the right tool for the right job, right? You won't, nothing is a panacea of amazingness, right? So very good question, but check out that slide deck. And I think maybe that video might be online somewhere. I can't remember. How much time we got? Oh, we got lots of time, 10 more minutes. Anonymous attendee, for thermal comfort mapping, it looks like the building was mapped in a fair amount of detail. How time consuming was this, and how do you think it impacts the scalability of potential rollouts? Very good question. So you kind of caught me. I think you caught me in a contradiction. I contradicted myself in a sense, because we did use a very scalable way of creating the data set. Handing people a watch, having them just walk around and fill out surveys on their daily lives is very scalable. But then mapping, yeah, you're right. Mapping that to the building information model, the way we did it, was tedious. It was time consuming. We wanted to show that it was useful. So that's why we did it. And I think we did show that it's useful, and at least in that context. But that study is not super scalable or generalizable because it's a single building. Like I bashed on case studies, but that was a case study, right? So we wanted the research community to take that and maybe figure out a way that you could, in a more automated way, take a BIM model, take GIS, and map it to, like, these Cozie microsurveys are a bunch of data with a latitude longitude. It has a GIS sort of lat longe, that marker, right? If there's a better way that we can map the spatial context in a more automated way, a faster way than what we did it, then it can become more scalable as a technique and more generalizable if you start applying it to lots of buildings. So very, very good question. We're chipping away at the problem one part at a time. And I think as a community, I want everyone to think about this as a trajectory, but don't immediately go and say, oh, all of our case studies are rubbish. No, don't do that, because they're probably very useful. We just need to kind of like steer the ship a little more in that direction, let's say. Very, very good question. And I see that, yeah. I see that the question askers are being added to, so if you guys want to say something, if in response you can, no pressure. Or have follow-up questions is fine. Don't be nervous. Next question, anonymous attendee. What are the steps to be a building data scientist? So there's two paths to being this hybrid thing, this hybrid skill set, which is building science and data science. The first path is to be a building scientist who has that strong context, who learns how to code, who learns coding bit by bit. The other path is to be a data scientist and somehow find your way into the building industry and start trying to apply your skills to that context. So I've seen both of these happen throughout the years. More common is the first example of a building scientist, I think, who learns some data science. Both directions they both have different steps, I would say. But I like to encourage the first type. The first type are these people that, there's so many smart people in our domain. There's so many great engineers out there who just know how to use Excel, right? They just use spreadsheets, and they're spreadsheet masters, right? We all know that person, or there might be that person. They love spreadsheets, they're very good at it. But learning this extra skill set, learning how to code, and just to process data to begin with and visualize it, not to do these fancy machine learning models. So that type of person, the steps that I would encourage you to take are to go to your job. Hey, Bob, where's that data set that we just gave up on because it's too crazy? It's too messy. We don't know how to hack into it. Go find that data set and start playing with it. Start trying to hack into it. Start trying to use pandas and whatever. Like that, I think, is the step. Other people might learn differently than me. So maybe somebody wants to take a course or read a book or something first before they do that, that's fine. Everybody's path is, I think, going to be a bit different. But I really encourage people who have that context skill set, because my definition of data scientist, a data scientist, by definition, is somebody who has contextual knowledge. You can't be a data scientist unless you start learning about the context you're trying to apply the stuff to. So people from the built environment, from data science or from building science, we have the context. You have that context already. You've already have that head start. There's a great book called Doing Data Science, which is all about the different skills you need to be a data scientist. There's like 6 of them: mathematics, statistics, computer science, machine learning, visualization, and context. And no one has all 6 of them. No one is maximized in all 6. So you also need to surround yourself with people that complement your skill set as well. Anyway, that's a very rambling answer. Hopefully it helps. Last but not least, last question we have today, Bianca, thanks for the question. What are your thoughts on progressing from prediction to control in buildings and the context of scalability, generalizability problem, transitioning to the autonomous vehicle in the building context, if you will? Excellent question. So everybody here who's ever worked in a real building control system knows that scalability is your first challenge, right? We all know that every building, the BMS of every building is this like special, in 1995, they built the building, they installed the system, they have this computer that runs it. No one touches the computer because John, who left 10 years ago, was the only one who knew how to use it, right? Like there's this thing that happens. So we have these silos, these data silos. That to me is by far the biggest challenge, by far. And you have things like the brick schema, you have Project Haystack trying to fix that paradigm. That's the first problem you have to encounter. I think that's doable. I think we're working on it. Then once you get that to happen, once you have this kind of layer of interoperability across buildings, that's when I think the magic happens. You've got all these interesting data sets that you can pull from lots of buildings. You can create models. You can have, that's where the generalizability comes into play, because then you have a diverse and large enough data set possibly that you can create models that have that generalizability factor. And then coming back into the control system, let's say you want to optimize your chilled water set points. Let's say you want to optimize your schedules. I think that's where the magic's going to happen when we get that layer of interoperability working. I personally, because cars don't have that problem, like Tesla doesn't have that problem, right?
Yeah, they have a standard system that they're working from, whereas you're saying like the buildings are bespoke, right? So in addition to the buildings, there's the HVAC systems. And I've been thinking about this problem of scalability and just the magnitude of the problem. Like, yes, definitely this first, not even having the John there to have the knowledge. Like I've run into that many times. So like that framework is definitely needed. And yeah, it's just I agree with you. That's like a really big hurdle.
And that's what the team that did the Great Energy Predictor competition, we talked afterwards a lot about, let's do another competition that is a labeling prediction competition. So can we label, if we have this building full of BMS points, can we automate that process? Can we use models to automate that process of labeling the building so it's not the brick and haystack give us the tools to make consistency across the building stock, but we still have to implement them. We still have to brick the building, right?
Yeah, exactly. How do you create that structure, that mapping for that particular building? Right.
So machine learning, that's a really great application for machine learning. So that's what I think that, and I would love to do it. We pitched it to, I think, ASHRAE, one of the ASHRAE committees that focuses on BACnet and brick and stuff. And they were like, great idea. But like, that's going to take like 4 years, for us to do. And we move slowly and all. So I'm like, okay, well, I don't know what we're going to. So anyway, if anybody out there has, like that's a really great challenge. Yeah. Huge challenge. So thanks for the question. Thanks for the discussion.
Yeah. I'll send you an email.
Yeah. Great. Sounds good.
We are at time and this is perfect. We finished all the questions and we still have, we can let you go at 7:30 a.m. That's great.
Perfect.
So yeah, thank you everyone once again for joining us. on our webinar series. If I posted the links, if you want to be part of the research committee and part of the webinars working group in selecting the speakers and organizing these every month. Next month, we're going to have Aziz Mbaye from Université Polytechnique, Montreal. He's going to be talking on how to model VRF heat pump systems. His presentation won the Best Paper Award at the ibpsa-usa conference, BPAC's conference last year. So looking forward to seeing some or all of you at that as well. That will be on the last Thursday of February. So that is the 23rd of February at 12 noon Pacific time, 3 p.m. Eastern, or 1 p.m. Mountain time. Yeah, unless, oh, I see in the slide, Clayton Sultan Nagy is also mentioned. He's also presenting probably in May for the series, but that's great.
Yeah. Good idea. Good idea.
Yeah.
Yeah, he does some great stuff. That controls integration stuff. He's really on top of that. That's really cool.
Wonderful. So keep an eye out for that webinar as well. That'll probably be in April or May as we get the dates decided. So unless anyone had any closing comments, I'm going to thank our speaker here, Clayton, once again. Thank you so much. And as I end the webinar, we're all going to get kicked out. So happy Thursday, happy Friday for some of you. Bye-bye.
Thanks, everybody.
Bye.